thank you everybody for being here for this yet another session of the periodic seminar that we are resuming today. Again, these seminars are held once every 2 weeks. Please, to those that have not yet filled the form, do it as soon as you can. Today, we had the pleasure to have the talk given by João on XDense, so on wireless network sensors. 45 minutes.
It's wireless.
Okay.
Thank you for coming. So I will introduce what I have been doing here as my research since I came to CISTER, not only, but what else I can also do. So the name of my work is XDense. We call it XDense, which is a grid sensor network for distributed data processing and feature extraction inside network. So I will talk about what dense sensing is, some applications, how to enable it, some related work. So our proposition and what's next, so what we are planning further. So actually, thanks to MEMS, nowadays there are plenty of sensing technologies which are very, very in small scales and very diverse. So we have all kinds of sensors for direct or indirect measurement. So for instance, this sensor here is for measuring flow speed, airflow speed, but using some hot wire. So you measure actually due to the heat transfer, you measure airflows. This is some capillary sensing. So you have a light beam going through this thing here, and then you measure the deflection of these pillars here to also measure flow speed. So you have also flexible sensors and that. This is well developed technology nowadays, but there's still some they lack on some solutions for actually getting data. So this is what my work is about. So there are other applications which we rely on. So avionics, for instance, probably the biggest motivation we had. So I was presented to this problem inside the avionics context. I will explain more or less what. And also biomedical devices, imaging, and robotics also benefit from this kind of sensing. So for instance, using those kinds of sensors in avionics, so if you are able to deploy as dense as required, you could have pictures like this of the flow. So this picture here, you see it's a simulation, computational simulation, and what you see is, so the air comes from this side, and in a given point of the wing, the air which was laminar becomes turbulent. And in this region here, drag increases a lot, so you waste energy. So this is something you want to reduce or to minimize in order to save energy and fuel. And then, but this is done only offline, so you have to simulate this. So if you could deploy enough sensors to make this picture in real time, that would be good then. Also for structural, this is for airflow monitoring, but it could be applied to structural monitoring for measuring acceleration, for instance, and so on. So this is some news, recent news from August 2014. Some state of the art, so developed by these people here. So have something like a human skin on aircraft. Also recently NASA came with this morphic beam, so it changes the angle based on in order to minimize drag and optimize the flight. And if you see here, they put on some strips to measure how the flow goes, and instead of having such sensor deployment, so it's still kind of hard to measure enough density, this kind of phenomenon. Other applications we see in, so for instance, recently China came with this supersonic submarine concept. So they want to actually exist already in torpedoes and so on, so actually they create some bubble around the submarine or the whatever is going through the water. So they control this bubble. So this dense deployment of sensors could be also used to have some feedback of what's around a submarine or a torpedo. It could also be used for this kind of wind turbines to set up the field and some parameters to increase efficiency or energy generation. Other application examples, so biomedical devices, some implants, these are brain implants for it's a retinal prosthesis, so actually they stick it behind the eye, so actually you have input of stimulus behind the eye, and then you put it inside the brain, so you, like for blind people to see. Also for electroencephalography, so you have this kind of deployments. And getting data out of this is kind of hard because you have one acquisition point for each of these sensors. Here you have shared buses or horizontal and vertical scanners, imaging systems. So you have these arrays of mirrors which are also coordinated using these vertical horizontal scanners. And also for robotic skins, so these skins are also mostly using this kind of technologies to have these deployments. But this is not much scalable, but I will tell why. And then to enable such deployments on airplanes, you need to have high density. So for instance, you have to have deployments of 0.1 millimeter distance sensors if you want to depict the structures of turbulences and the vortices on top of wings, so you can distinguish what's laminar, what's turbulent, as I've shown before. And also on scalability, because you have to be able to grow these networks all over the aircraft, and maybe if you use shared buses or wireless, you might have some interference issues and concurrency, and then you flood the network with data, and then processing starts getting, the centralization might create bottlenecks and high processing times. But this is more or less what it would be, how it would look like. And so these are the issues I just talked about. So you have to be able to scale up, you have to be able to deal with high quantity of sensors. So you have to be able to extract data efficiently and on time. So if you have to have a closed loop, it's important to have time guarantees and predictability. So related work, there is this effort done by this Joshua push pin computer, so he uses a substrate which has the power supply for these nodes. And these nodes actually have infrared communication among them. So, but what happens is that they have only one receiver and one transmitter, and it's wireless communication. So there are concurrency issues, and then yes, and they have only one transceiver. So, which means that you cannot really talk in. So you have concurrency. So you cannot talk in with more than one node at a time, so extracting data becomes costly. So communication is not as cheap as it should be for such dense deployments. Another example from the authors is this, but these are sensors. So you measure contact. So it's like a skin, we call it electronic skin. And they replace infrared by wired communication. But it lacks on the same issues because you have a single communication port and concurrency issues because of shared buses. So what we are proposing is this architecture which we call XDense. So it's a mesh grid network in which each sensor has 4 network devices which are ports connecting them to each of the 4 neighboring neighboring nodes. It has one switch which interconnects the net devices, so the nodes could be able to forward messages without processing them on the hardware layer. So and then on the upper layer you have a processor, a microcontroller, which runs the protocols and whatever the programmer, the user requires to. And back to the hardware level again, you have the sensor, which can be any kind of sensing. So in the avionics applications, you could measure pressure or like I said, heat transfer to understand the flow and so on. In the microcontroller, we represent here different applications. So for instance, you can have edge detection and others which I will show later on. And just to here in our model we use two different queues on the transmit port, TX for different priorities. So I will explain again later on why we did like that. So what our objective is to have local data communication with very low cost, so it allows us to have distributed processing to minimize data transmissions towards the sink. So you should have one sink which is then connected either to a supervisory system or to an actuator if it's a closed loop. If it's a closed loop system. So if I'm not clear, please ask me at any time, whatever you want.
Why you decided to use this mesh architecture for the network? I mean, is there a justification on the way that the data is acquired, or why?
And so when I was presented to this problem, it was for this active flow control. So, and then first of all, I thought, okay, wireless might make sense, but not for each node. So the deployment is too dense. You cannot afford to have batteries or things like this. Okay, so let's go to wireless. But then if you have thousands of nodes, maybe millions, and then you have a shared bus, and then concurrency issues. So how long would you take to sample the entire network if you have millions of sensors. Okay, so then something else should be done. So, okay, how can you explore, how can you increase the distributed processing capability of the network by having local data communication and processing? And then we thought that this could make sense just as it does in network on chip and so on. So to maximize these opportunities of distributed process. Does it make sense?
Yeah, my question is like why you are choosing mesh and not other kind of network architecture, right? Like you can derive some performance like Torus or something else, right? I'm saying why mesh?
Yeah, okay, so it could be, like you said, Tor, so we could connect this to that node, or there are some variations that could be done, but okay, but we first came to the basic one, which is this mesh. But if you think of a Torus, let's say, which you could connect this node to that one, but what if it's a no-wing? So you are really deploying it in no-wing, so can you afford to have a wire coming from all the way from one side to another? So it's an issue of wiring and deploying, so it's a more practical issue.
Okay.
In a network on chip, things are like this big, but here it should be wider. And then one of our objectives with this is to guarantee this, that increasing the network, the overall latency should keep low. And how does it work? So we have basically three protocols and working states of our network. So first the sync, I will pass through in the next slides, but mostly any node can be configured as a sync. So if you are the sync, you announce yourself to the network to show where you are. So you perform network discovery. If you are not a sync, you wait for a network discovery, at least one, so you can have more than one sync. So then you know where the closest sync is. After that, you keep on sharing data with your neighbors, and as soon as you process the content of your neighboring data, and then you detect or not some feature of the phenomenon. So, for example, so the packet content is basically this. We keep track of location, because as the nodes forward the packet, they increase or they change the value of X and Y. So you know where the sync is. The payload is sensor date and these things, and a serial number just to avoid redundant data. So that's how it works. So that in this case here we have a sync in the center. So it performs the network discovery. The packet goes all over the network. So I'm trying to show this, like it goes up, but it also reaches this node here, either from here or there, whatever the path is, using a simple protocol in which the nodes receive a packet and they transmit to the three other ports of it. So all the nodes will know where the sync is. Next step, they keep on changing data with neighbors. So this would be the neighborhood of this node here. And neighborhood size here is 3 because there are 3 hops away. So, which means that it gets data from up to 3 nodes around him, and its data goes to up to this guy as well. So each node will have, so let's say this node here will have a similar neighborhood, but actually here instead of that one. So you have some data to process. And if the result of data processing is significant enough, you then announce it to the sink. So what you have found. For having as least as possible transmissions to the sink to avoid contentions and so on, but it can also happen. So then there will be some queuing on one of these nodes. After that, they switch back to state 2 event monitoring, which I call it. So for doing these simulations, I developed this NS3 model, which is basically, which are these files here, which tries to abstract these layers, which are the network devices, the switch, the sensor, and the application layer. And actually the sensor is an abstraction which I've done, which also connects to external data. So I'm able to, let's say, get data from a CFD, a fluid dynamic application, and feed my sensor network with that. So I will show the results we have achieved so far, which are mainly two. First, for data aggregation and compression on network and distributed feature extraction or edge detection. So what we thought was, probably if you have a sensor network, you first want to get data from all the sensors. So if each node transmits to the sink, so then I simulated the 101 by 101 network with one sink in the center. So, and then what if all the nodes transmit to the sink? Then you have a big jam. Then you have basically to wait all the packets to reach the sink. Then, which leads to high latency. But then, what if we define neighborhoods like this, in which only the node in the center transmits some compressed data from its neighborhood? Then you can decrease latency end-to-end delay, but you lose resolution. So that's what we want to show here. So we increase these neighborhoods up to n hops equal 5, but then trading off between resolution and time. I will show the gain on end-to-end delay. And this is the input data we use. So this is a CFD, computational fluid dynamics simulation, which simulates a flow, an airflow coming from a nozzle here and blowing some hot air on a free space. And actually, so this is what. And why did we choose this scenarios? Because it's a very common issue to try to figure out this boundary layer, so which is what separates the turbulent from laminar flows. So laminar flow is the free space, which is the air which is stopped there, and the air forming these vortices is the turbulent flow, which is more or less the same phenomenon that we see in the wing of an airplane. So this is the results in terms of time. So if we sample each sensor node, we would have to wait 2,500 time slots in which it can be reduced to down to 500 if you increase the aggregation neighborhood. And here it's just a zoom inside this beginning here. This is the number of packets received by the sink, so which means that increasing the neighborhood size, you decrease the number of packets transmitted to the sink, and you decrease end-to-end delay. And this is the trade-off. So here it's the error on the mean square error on the data received by the sink and the end-to-end delay. So there is a trade-off between, so as I shown on those pictures there. And these are queue size, which is also for those two different queues I've shown earlier, and for the two different protocols. I'm not sure if it's as clear. And then last, I used an algorithm for edge detection to determine the interface between laminar and turbulent flow. Just in case you are not interested in sampling all the data, but only figuring out where this boundary layer is. So I use some image processing algorithms for edge detection inside the network. So the nodes perform these computations, and by varying the neighborhood size from 1 to 5, we have these different results. So smaller neighborhoods lead to bad detections. As you increase it, you lose some definition of sharp edges like this, but you have more robust detections. And by doing that, you drop the time to acquire data from 2,500 down to 200 time slots, which is a huge gain, which makes sense in case you don't want to sample all the nodes and you don't have time to do that. And the raw data is not important, but the pre-processed. So another simulation we did was using this jet. We wanted also to determine the envelope, so the region that separates turbulent to laminar flow. So this is a real flow using a capture using a camera by other authors which we used. So he proposed some techniques to define this envelope, and using our algorithms inside the network by the nodes, we were able to get close enough. So this is the envelope our nodes found using in-network processing, using a neighborhood size of 3. So we feed our network with this data, and our node detects these regions here. So this is the error of our findings with different neighborhood size, which is basically, we can say that 80% of the nodes have error smaller than 4%. And the error is quite small. And the last experiment we have was just to show that, okay, for different scenarios, different dynamics, different phenomena, our network behaves differently as well. So for laminar flow, not much things change over time. So this is how it looks like, and this is turbulent flow. And then what happens is that on laminar flow, the number of transmissions over time drops since nothing much new is happening. And in the other hand, with the turbulent flow, this rate keeps it's higher. So because of the changing of the phenomenon, the dynamic of it. So right now we are developing some prototype to validate it in reality. So this is the nodes we have right now, and this is how more or less the network should look like, but bigger. So, and for this we are using a Cortex M4 from Atmel connected to four serial ports, the neighboring, so for each one of the directions. We have an extra serial port here for debugging purposes. We have 4 RGB LEDs for signaling and possibly showing some actuation. Sensors, there is pressure, this is light, this is acceleration. So we want to validate some concepts of structural monitoring and airflow monitoring. And with the light sensor, our objective is to be able to simulate any kind of input in our network. So I should be able to take these nodes, put it in like in front of a projector like this, and from the projector I project some data from some capture from many phenomena. So I can, using light, I can emulate the input of other, let's say of an airflow. But many questions are still open. So what features can I expect in which other scenarios? How to make it independent of the sensor? So how to dimension the network? So the timing requirements of the application, how to match it with the network speed and processing and so on. What to compare it with? So it's hard to have some other approaches as base of comparison. What metrics to use? How to do timing analysis of this kind of networks? And what other scenarios can we explore with this? We find it has a potential, but we still have questions of what and where to apply it. And that's it. So if you have any questions, just let me know.
So, any question?
You said that you have a lot of data to process, right?
Mm-hmm.
That you have some compression techniques to produce that data. Do you think that there is still room for more improvement? Do you think that there are other compression techniques that we can use? And just to track that boundary layer. Do you, I mean, my question is like, do we really need that many sensors, or maybe there is a compression technique that allows you to reduce the number of sensors or make it cheaper to deploy?
So actually, this, to answer that, I would need to have more basis on the phenomenon itself. So I have to do it at a given point is to study how the phenomenon looks like. So this separation layer, when and how it happens, how dynamic it is, even to dimension sampling rate and transmission rate, baud rate, and these things. And maybe I could answer your question, but I'm sure processing techniques, I'm sure that there are better ones to be explored and new ones. But these require a deep understanding of the phenomenon, so it's hard to tell right now how would look like.
Question? Then maybe I will ask a question. Do you already have some hints on how to address the timing analysis for real-time applications?
I've been discussing this with some with Ali. I've talked with Vincent as well. Some ideas of how to do that, but let's say our last conclusion is that we need to be able to bound it, because it's so pessimistic, the analysis we have, that we have to define a bit the protocol, or if it's synchronous or asynchronous, how it works, or how it should work too, so we are able to determine timing and so on, because it's too free right now, so you probably have to limit it a bit to be able to bound. Otherwise the predictions or the analysis are too much pessimistic, and they are kind of meaningless.
Will it be dependent on the platform itself, the topology that you are using? Or?
It depends on the number of nodes, the number of sinks, but because the issue is when you are sampling, so the nodes react based on the data they get. So you cannot really predict when they are announcing something. So if they announce or event they found based on the data they get, you cannot really say how many nodes will announce at any time. So you don't have much information of how it will behave, neither regarding time. So maybe you can specify sampling rate, but are they transmitting at the same time? Right now it's asynchronous, so it can be good, so it offloads the network, but it's hard to predict. It's even harder to bound
And why you don't make it synchronous then?
Yeah, it could be synchronous, but then I have to propose also some clock distribution or some synchronization mechanisms, and I have to see what the trade-off is. So maybe we lose more than maybe we are able to predict better. So this has to be studied.